If you are at college or university and you are studying electronics, don't miss most of your video presentations on some of the critical topics that are covered in your Electronics 1 course. And it is my hope that you are enjoying what we are giving you on this channel of yours. Enjoy. Welcome to our 7th video presentation, and at this time we are going to look at clippers. This is an important application of a PN junction diode. It is my hope that you are benefiting from these lectures, and if so, don't forget to like and to subscribe on this favorite channel of yours. My name is Motion Marufu, and for any comment or suggestions, don't forget to get in touch with me on motionmarufu60@gmail.com or via WhatsApp on +263 717 535 866. Guys, let's enjoy. These are some of the objectives which you find in your electronics course when you are studying clippers, and they are: you must be able to define a clipper and with the aid of examples, and also using a circuit diagram must be able to describe voltage waveform operation of different types of clippers. Then the last but not the least objectives is you must be able to explain with the aid of suitable diagrams practical applications of clippers. Then a very important point to take note of, you must make sure that you have gone through the video presentation on diode circuit models, forward and reverse biasing of a diode, and also your electrical engineering technology or circuit theory basic concepts. If you haven't, do so, because you'll find them handy in this interesting application of PN junction diode as a clipper. What is a clipper? A clipper is simply a circuit that removes or clips a portion of the input signal, and it does not distort the remaining part of the waveform. That is a clipper. It has got some other names like voltage or current limiters, amplitude selector, because you find that it will allow a certain amplitude to pass through and slice off or clips or removes the other part. It is also called a slicer, and these circuits are found in digital electronic systems like in our calculators, in our computers, radio and television receivers, and even in radars. And most of the clippers employ PN junction diodes in series or in parallel. Another name for parallel is shunt. So they are known as diode clippers. Types of clippers. We've got basic types, and these are a series clipper whereby the diode is in series with the load. Then we've got a parallel or shunt clipper whereby the diode is in parallel with the load. Let's look at what a series clipper is. This is when the diode is in series with the load, and as I've said, a parallel clipper is when the diode is in parallel with the load. In your electrical engineering technology or circuit theory course, you must have covered series and parallel circuits of resistors. If you haven't, don't worry. In one of the videos, you'll find this well covered. And it's all along we have been talking about a half-wave rectifier, which is a basic clipper circuit that eliminates one half of the input signal and does not change the remaining half. And please take note of the following. Each series clipper contains a diode in series with the load, and a parallel or a shunt clipper contains a diode in parallel with the load. Schematic diagram of series and shunt clippers. You must be able to draw a negative series clipper as well as a positive series clipper, even a negative shunt clipper as well as a positive shunt clipper. If you have understood half-wave rectifier, you won't have a challenge here. why are we saying this is a negative series clipper? When the input is positive, this diode is going to be forward biased and current is going to flow through the load resistor, and we are going to have an output. When the input is negative, this diode is not going to flow and there's not going to be any current flow, hence the output will be 0. In other words, we have sliced the negative half cycle so that we will have only the positive half cycle. Hence we are saying this is a negative series clipper. Take note of a positive series clipper. We have changed the direction of this diode. And what is going to happen? As long as you have understood half-wave rectification, there is no challenge, or even the operation of a diode. When the input is positive, this diode is going to be reverse biased because of this negative or because of this cathode. So this diode is going to allow no current to flow through the resistor. Hence, there will not be any voltage across this resistor. As long as there is no current flowing across this, we won't have any voltage drop. Hence, we've sliced off a positive half cycle. But when the input becomes negative, the negative is going to repel majority charge carriers, hence we are going to have a current flowing, and this is going to result in a voltage drop. In other words, we've sliced off the positive half cycle and we are now left with the negative half cycle, hence this is a positive series clipper. For a shunt, please take note, your second theory is being called here. When the input is positive, this diode is going to be reverse biased because the positive and the negative, they attract, hence it is going to be off. So most of the current is going to go this way, hence we are going to have an output. But when the input becomes negative, this is going to be forward biased, and assuming it is ideal, it means this is going to be a wire, and the voltage across this, and we know if it is a wire, it becomes a short circuit, and the voltage across a short circuit is 0. And since this is connected in parallel with this, it means the voltage across the load is also going to be 0, which means we have sliced the negative half cycle, hence the name negative shunt clipper. The same applies as long as we have understood the operation of a PN junction diode. There is no problem. When the input is positive, this diode is going to be forward biased. But please take note, it is in parallel with the load. Assuming an ideal diode, this will be a closed switch, it will be a wire. So the voltage across this is the same as the voltage across this for parallel connected devices. Hence, the positive half cycle will be 0. In other words, we won't have an output. But for a negative half cycle input, this is going to be off. Most of the current is going to flow through the load. Hence, we are going to have an output. So we are remaining with the positive half cycle, and we have removed the negative. In other words, we have removed the positive half cycle, and we are now remaining with the negative half cycle. Series negative and shunt clipper. What is happening there? What is happening there? Please take note, the voltage across the load VL is equals to Vin, which is our AC input, minus the drop across the diode, which is VF or VD or cut-in voltage. It means we are assuming a practical diode from, if you can recall this from our previous lecture. So for a negative series clipper, as you can see, this is our input, but we have removed the negative half cycle. So we are calling it a negative series clipper. Series because the diode is in series with the load resistor RL. and we are saying this peak, the output peak, which is the maximum voltage, is equal to the input voltage minus the drop across the diode, and this is the zero line. So we are saying the negative half cycle will not produce an output at the load, hence it is the one we have removed. So we are saying negative series clipper, and it is written the diode is forward biased during the positive alternation or a positive input. Right, let's go to this diagram. We are saying this is a positive series clipper. Why? Look in the direction in which the diode is pointing. If the input is positive, this diode will not be forward biased, rather it will be reverse biased, hence no current will flow through the load. As long as there is no current flow through the load in this setup, it means the diode, it means there will be no voltage across the load resistor RL. In other words, we clip the positive half cycle as shown. We clip the positive half cycle and only remain with an undistorted negative half cycle. Please take note that when the input becomes negative, this diode is forward biased and current is going to flow, assuming conventional current flow is going to flow in this direction, because if this is negative, obviously this is positive. Hence, for a negative half cycle, a negative half cycle input, the diode is going to be forward biased, hence we are going to have a current flow through the load resistor RL and an output. And this output, please take note, because it is negative, it's minus, so it's going to give us a plus, hence this will be our negative peak. So please, you must be able to explain the operation, and also using the waveform diagrams, you must be able to explain the operation, like negative clipping, which means that we are removing the negative part of the input and only remain with the positive part. This is the positive part. From there to there is positive, then from there to there is negative, then this is our zero line. So we are clipping this. In other words, we are removing this so that it will remain at zero. Zero means we have nothing. And please take note that the remaining positive part, according to this diagram, it has got the same amplitude as the input, but on this output it is less than by 0.7. This 0.7 is assuming that we are using a silicon diode as a clipper, hence VF cut-in voltage or the drop across that silicon diode is going to reduce the output by 0.7 according to Kirchhoff's voltage law. Even on this triangular waveform, we have clipped off the negative half cycle and it's now 0, and this is less than this by the drop across the clipper, which is a diode. This is a sinusoidal signal. This is an alternating current signal. In other words, we have clipped the negative half cycle and it's now 0. And this is less than this by the drop across the clipper, which is 0.7. So it is not, it doesn't have the same amplitude as this. On this, we are assuming an ideal diode, and you can see at the column. So this is generally showing you how a negative clipper operates. There's no need to repeat this for a positive clipper. It will do the opposite. In other words, it will clip the positive and leave the negative half cycle undistorted. Positive shunt clipper, we are saying it clips off, it removes the positive half cycle of the input and does not distort the negative half cycle. This is the positive half cycle of the input, this is the negative half cycle of the input. So these are the ones that are not distorted, and these are the ones that are removed as shown. These are the clipped parts. And how does that happen? When the input is positive, this diode is going to be forward biased, assuming it is an ideal diode. It behaves as a wire. which means it is going to short this out, or the current is going to flow this through this diode, because it behaves as a switch, as a closed switch, as a wire. So we know from our EET or circuit theory, the voltage across a short circuit or a wire is 0, and voltage across a parallel circuit is the same. So if this is 0, it means this is 0. Hence, we are clipping the positive half cycles. When the input becomes negative, this diode is reverse biased. Hence, all our current is going to flow through R and through RL. So it means we are going to have an output. Hence, an output is therefore negative half cycles. That's the way how this thing operates, and you must be able to explain as I've done, or even better. I've gone through the operation of a positive shunt clipper in the previous diagram. Go through it and see if it agrees with what I have explained. Negative shunt clipper. Why shunt? Because this is in parallel with our load RL. Why negative? Because this is clipped or removed. So you might decide not to show this. You just go, when the input becomes negative, it just remains at 0. And when the input is positive, we have a positive output. And when it gets to 0, it just remains there. So I'll go through the operation of this circuit, and this time I'm going to be very fast. This is my input signal, both positive and negative half cycle. So I'm saying when the input is positive, this diode is going to be reverse biased. Hence, all our current from the source will proceed through R and through RL, and none will go through this. Hence, we are going to have a full output voltage that is equal to the positive half input. When the input becomes negative, this diode is going to be forward biased, and assuming it is ideal, all our current will pass through this because it will behave as a short circuit. It will short this out, hence the voltage across this is the same as the voltage across this, hence the output will be 0, since it is in parallel with the closed switch, which is this diode when it is forward biased. Hence, when the input is negative, we are not going to have an output. So for all these negative inputs, the output will be 0. That's the operation of a negative shunt clipper. This calls for your electrical engineering technology or circuit theory that voltage across a parallel circuit is the same, and this is the concept that we are using. We are going deeper and deeper. We are now looking at biased clippers. The biased is coming from the fact that we have added a reference voltage. We have added a reference voltage, and we are saying this circuit shows a biased positive clipper. We want to see whether it is going to clip a certain part of the positive half cycle. Let's see. So we've got a series, a biased positive clipper and a shunt biased positive clipper. Shunt, why? Because normally we connected the load at these points, hence we say this is in parallel with the load, hence the word shunt. Biased because we've got a reference voltage that we have added. So these two, they operate the same. I hope I'll be able to explain them very quickly. All right, let's look at what happens. Right, when the input is positive, this diode is going to be reverse biased and no current is going to flow through this resistor R. But if you measure the voltage across these terminals, if you measure the output voltage, if you put your positive there and your negative there of your voltmeter or your multimeter, you will measure a voltage that is equal to VR, even though this is reverse biased for a positive input. So what are we saying? We are saying we are clipping this part only from there to there, and we are going to remain with this up to this level, then it goes straight. And also, when the input is negative, this diode is going to be forward biased and a current is going to flow through the load. Hence, we are going to have an output for the whole input half cycle. So it is going to go like this. At this point, it's going to go up, get to VR, it's going to flatten, and it's going to go in the negative direction. So in other words, for a biased positive clipper, we only remove a certain portion of the input waveform. Let's go to this and see whether it operates the same as the series positive clipper. For a positive input, this diode is going to be forward biased and current is going to flow in this direction. So if you measure the voltage across this, if you measure the output voltage, you find VR. You find VR. So this is going to follow the input. When it gets to VR, it is going to flatten, since this is the maximum voltage across the output. Hence, these two, they behave the same. Hence, we are calling biased positive clippers. Go through that slide on your own and see if it agrees with my explanation. Biased series negative clipper. Why biased? Because we've got a reference voltage of V. Why series? Because this is in series with R. Why negative clipper? Because this removes or clips off the negative part. Let's see what happens. We are going to analyze this in steps. The first step or condition is when input voltage is positive but it is less than V. When input voltage is less than V, this reference voltage will reverse bias this diode. So as long as input voltage is positive but is less than V, this diode will remain reverse biased, hence it will not conduct. So the voltage drop across R will be 0, hence the output voltage will also be 0. This is the equivalent circuit or the circuit model of this diagram, and it is showing that for when Vin is less than the reference voltage V, it means that your diode will be off, hence there will be 0 voltage across R. Guys, these things are very interesting. We are now looking at the other condition, operation when Vin is positive, but it is now greater than V. What is the effect? When this is now greater than V, it means that the diode is going to be on. It will behave like a closed switch, hence D on means diode on, hence it is going to behave like a closed switch, and our current is going to flow this way. Hence we are going to have an output that is equal to Vin minus V, where V is this voltage. If you can have a look, these two, this will oppose this, so this diode will conduct when this is greater than this, or when it is able to overcome this. You know what happens with the barrier voltage. Hence we are going to have an output. Please, let's have a look at our output. We are going to have an output only when Vin is greater than V, hence from there to there only. When it is now less than, we want to have an output. Hence we are saying this is a biased series negative clipper, because we don't have the negative part. It has been clipped off. We are now going to analyze a biased series negative clipper when Vin is negative. And when Vin is negative, according to the circuitry on the previous slide, it means that the diode is going to be off. And when the diode is off, what does that mean? It means that it is reverse bias and therefore remains off, and our output will be 0 since no current will flowing through R. That's the analysis when the input voltage is negative. It means that the output is clipped off. Now a look at the biased series positive clipper. Why biased? Because of the V. Why series? Because these two are in series, and we are saying we are clipping off the positive. Let's see. And just as we did in biased series negative clipper, we'll analyze this in parts. And we are saying the diode is cut off during the entire positive half cycle, because yes, it will be reverse biased. Alright, let's analyze it when Vin is less than V. The input voltage is less than V. This diode is reverse biased because this negative half cycle is connected to the cathode. Hence, it behaves as an open switch. Hence, the output will be equal to 0. Take note, the output will be equal to 0 for Vin less than V. let's analyze it for V in greater than V. When our V in is greater than V, the diode will be reverse biased again, and the output will be 0 again. Why? Because when this is greater than V, it means that this diode is reverse biased even by V. Hence, the diode will be off. Hence, the output will be 0. A biased parallel negative clipper analysis. There are two types: a biased negative parallel clipper as well as a positive parallel clipper. We are going to look at the operation when V in is positive, and this is our circuit diagram. And we are saying for a positive input, this diode is going to be reverse biased, hence it will behave as an open switch. Hence the output voltage measured between this point and this point is the same as measuring this point and this point. Hence V out will be equal to V in for V in positive. A biased parallel negative clipper. Why biased? Because we have got a reference voltage of V. Why parallel? Because this is in parallel with V out. Why negative? Because it clips off, it removes the negative waveform, and we are going to analyze it in parts. For when V in, which is our V in, is negative V, when V in is less than V, right, the diode is forward biased, and it is forward biased by this voltage, and the output voltage will be equal to V because it is in parallel with this V, and this V forward biased this diode, and this is the equivalent circuit. This, assuming it is an ideal, it behaves like like a closed switch. Hence, you'll be measuring the voltage across this supply of V. Hence, we say our V out will be equal to positive V, because of the orientation of V. We are now going to analyze a situation whereby V in is negative but is higher than V. V in is negative but is higher than V. When V in is negative, it means that according to our diagram in the previous slide, our diode is going to be reverse biased. Hence, it is off. It is off. Hence, when it is off, it means that if you measure the output voltage, between this point and this point, which is the same as this point and this point, you'll be measuring the input voltage, not the voltage across V. So in other words, we are saying, even though the diode is reverse biased as it is, your output voltage will be equal to V in as shown. So we are saying we have got a negative output since our input is negative. Operation for V in negative but is less than V. Our diode is going to be forward biased, hence it is going to behave like a closed switch. If you may, please take note of the polarity. Negative is up there and positive is down there. So when you measure the output voltage for negative input that is less than V, you will find an output voltage that is equal to this voltage, which is minus V. It's minus because the minus is above. Hence, you can see the minus there and the minus there. So your output voltage will be minus V. Guys, you must be able to analyze even better than I am. We are now going to analyze a situation whereby V in is positive and is higher than V, where V is the reference voltage. And we are seeing that under such a scenario, which is this, the diode is going to be reverse biased, hence it is off, hence your V out will be equal to V in, since you'll be measuring between these 2 points, which is the same as between these 2 points. Your output voltage will be equal to your input voltage. But the operation for negative, when V in is negative, or for negative values of V in, your diode will be forward biased, and if your diode is forward biased, it means that your output voltage will be equal to V in, because this will be behaving as a closed switch, which is a wire. Hence, if you put your probes of your multimeter between this point and this point, you are going to get a value of V, which is positive. Biased double clippers. This is very interesting. Look at the connection. This diode is looking downwards. This one is looking upwards. Look at the V1 and V2. This is reverse biasing this, and this is reverse biasing this. So we want to analyze and come up with the output waveform. to see which is clipped, which is not clipped, which is not distorted. Operation in the positive half cycle. And we are saying when the input is positive and V in is less than V1. Please take note that you must put that condition. V in is less than V1. We are saying D1 is reverse biased for the entire duration of the positive half cycle. Therefore, our V out will be equal to V in when V in is less than. What we are saying is V in, this is positive half cycle. The positive half cycle must turn this diode on, but it also turns this diode off because of the cathode, which is facing upwards. But our V in is less than V. When V in is less than V, it means this diode is reverse biased. The same applies with this diode. So our V in will not be the voltage due to D1 or D2, but it will be due to the supply voltage. Hence, we are saying V out is equal to V in. And we are saying as soon as the input voltage becomes higher than V1, this diode is going to conduct, while this is going to remain off, and the output will be equal to the voltage across this, and it will be the same as the voltage across this. Let's go to the next slide where we are going to see the equivalent circuit for the positive half cycle. The biased double clippers equivalent circuit when V in is less than Vf and when V in is less than V1 and also when V in is greater than V1. Let's see what is happening here. Or this one will be off reverse biased, this one will be off reverse biased, hence your output, if you put your multimeter between this point and this point, is the same with this point and this point because this is a wire. So if you put your multimeter at the end there, you are measuring your supply voltage, hence your V out will be, your output voltage V out will be equal to your positive input. But when V in is greater than or equal to V1, this diode is going to turn on. Hence, if you measure the voltage between this point and this point, it will be equal to V1. So your output will be V1. Let's go to the next slide and analyze the other condition that is going to affect D2. We've come to the end of our 7th video presentation for Electronics 1, and I hope, guys, you have enjoyed clippers. Clippers are very, very important, and you must have sufficient knowledge of Kirchhoff's voltage law, diode circuit models, behavior of a forward biased and reverse biased diode. Actually, I can say your diode basics. Otherwise, you won't be able to make it. Until then, guys, take care of yourself, mask up, wash your hands, get vaccinated, and let's meet in our next video presentation. We'll be looking at clampers. We looked at clippers, and in the next video presentation we'll be looking at clampers, and this is a diode application. Bye.